Hey, this is Robert Quimby, and I'm going to tell you about the KS test. So at some point in your career, you might come across two different samples that were selected randomly and independent of each other. And you might want to say, are these two samples drawn from the same parent population? So it turns out it's actually impossible to say if two samples are drawn from the same population. But what you can say is that if they were drawn from the same parent population, you can make this null hypothesis that they were drawn from the same parent population, then there are certain tests that you can do to falsify that claim. So you can say, no, they were not drawn from the same parent population, because if they were, something should be true. So this is what a KS test is getting at, and that's what we're going to talk about. So in this tutorial, we're going to discuss how you can determine if two samples are, not actually if they're drawn from the same distribution, but if they were technically not drawn from the same distribution. We can prove that. We're going to look at plotting histograms. That's a popular way to look at a distribution of data. And we're going to show that's not the best way to do it, that actually plotting cumulative distributions is much more revealing, and that's the way you should be doing things. And this is actually related to the KS test, so we're going to talk about that and how you can use it to falsify the null hypothesis that two samples are drawn from the same population. All right, so let's first start by creating just a random sample. So I'm going to have a sample with, say, 20 different data points in it. And for each one of these data points, we're going to have them drawn just randomly from a normal distribution. So we have to pick a mean value and a standard deviation for our sample. We're going to pick a mean value, just say, of 100, and we have a standard deviation of maybe 5. And so we can run this cell, and now we have ourselves a randomly selected sample that we know is drawn from a Gaussian distribution. Okay? So what does this look like? Kind of the most common thing that astronomers like to do is they plot a histogram of it. As we'll see, this is not the best way to do it, but it's very commonly done. So here you go. Here's a histogram of our sample, and again, we know this is drawn from a Gaussian distribution. But if you look at this, like, is it a Gaussian? It's hard to tell, kind of visually. One thing you might think to do is, hey, we can plot this with an actual Gaussian on top of that, and then we can use that to say if the kind of Gaussian model curve fits through the bins, then maybe it's a Gaussian distribution. All right, so let's set this up. Let's start by setting how we want to bin the data, because there's different ways to bin that data, and this is an important point. So we're going to take our sample that we just did this plot hist command a second ago, but we're going to change the range now. So instead of just letting plot hist figure out where to put the bins, we're going to tell it exactly where we want them. So we want it to plot it over a range that runs from, let's say, 5 standard deviations below the mean to 5 standard deviations above the mean. Okay? So we use the range keyword, and we set it from low to high. And then we can tell it how many bins we want. By default, it uses 10 bins, so we'll start with that. But we can play with this in a second. Then on top of this, we also want to draw a Gaussian distribution. So we're going to define a bunch of x values that just run from our low to high values. And we'll make 100 of those. We can make as many as we want. We're just drawing a curve. And then for each one of these x values, we need to calculate the y value for our Gaussian. So remember, a Gaussian is just an exponent of negative x minus mu squared divided by 2 divided by sigma squared. So, right, so this is defining our Gaussian, and this term in front here is our normalization. So we're going to normalize so that the total area is actually equal to the number of samples that we have. So we can plot both of these up now. Oh, and actually I forgot to close off that. So there we go. So now we have our histogram here of our random sample, and we have our Gaussian drawn on top of that. Now looking at this, again, is this Gaussian well represented, is this distribution well represented by a Gaussian? Maybe, but it's hard to tell. Maybe if we added more bins, this might help a little bit. So we can add more bins. Is that a good representation? Again, it's hard to tell. We can actually increase this more, and you'll notice that the more bins you have, the more they're broken up, because we have a small sample size here. So actually, by adding more bins, I could add a lot of bins, it gets to a point where you either have 0 or 1 bin objects in each bin, and it becomes really impossible to tell if it's a Gaussian or not. So we were learning that the number of bins you have actually is going to affect how well you perceive this model to fit. Another thing that we can do is we can actually change a range here. So let's go back to, say, 20 bins. All right, so we get something that's maybe kind of Gaussian, maybe it fits, but what if we change this range? If I just make a small change here, let's say instead of having our bins go from starting at low, let's have it start at low plus 0.5. Just make a small shift in where we plot, where we define each one of those bins. And if we replot, you'll see that this figure changes. So we can plot a different value here. And every time I change where we put the bins, the shape actually seems to change a little bit. You got to think about how this works. We have these bins that we're defining. It goes from here to here, and when we shift this over left or right, sometimes we'll get a sample in that bin that we didn't have before. So just by changing the range where we're binning, and or by changing the number of bins we have, we can get a different shape out of this. So it's actually, at the end of the day, it's impossible to just take a histogram of your data and then to do some kind of a fit using this Gaussian distribution to see if this sample is drawn from Gaussian distribution. So that's not the way we want to do things. So one thing we could do is we can just make the simple claim that, hey, if our sample, if we want to test if it's drawn from some parent population, and we know what the mean value of that parent population is, and we know its standard deviation, and we know its skewness, we can check our sample mean value and standard deviation and skewness. And if these values are reasonably close, the parent population's values, then we know it's drawn. We can't reject the null hypothesis that it was drawn from that sample. We would say that the samples appear to be consistent. Now, how do we define what is reasonably close? Well, we have to look at what the expected uncertainty in each one of these values is, and you could use uncertainty propagation to figure that out. So here we've taken 20 different numbers, and we just boil them down to 3 different numbers here. That's telling us something about our distribution, but it's not telling us everything about the distribution. To use all the information in the distribution in our sample, we need to use all the data points in that sample. So we need a way that actually uses everything, not just a few small metrics that we can pull out, or statistics that we can pull out. So a great way to actually look at the sample is by plotting its cumulative distribution. Right? So the way we plot a cumulative distribution is you start by sorting your sample. So we'll take our sample and we'll sort it. And this will put all of our values in order. So we'll have 95, 96, 97. Maybe I have repeat values. So it might be 95, 96, 96, 97, 98, 98, whatever. But they'll be in order. And now we're going to calculate the cumulative fraction. So for each value in our sample, we're now just going to assign a number to it. So this is the first value in order, second, third, fourth, etc. So we're just going to create a big array of numbers. We use NumPy arange, and we want n values. Okay, and we can actually plot this right now. And what you can see is that we have the value that we have from our sample. And then we can see that the first value is here, and then the second value is here, and the third value is here, and the fourth value is here. And it just steps up one value at a time. It steps up all the way until our last value here. This is 20, well, actually 19, because we started at 0 high. What is even better to do is to actually divide this by the number of samples we have. So we get a number that ranges from 0 to 1. And so this is giving you the fraction now of values that are at some point, like say 100 or less. So we know now, just by looking at where this intersects on the ordinate here, that about maybe 35% of our values are less than 100. Right? So 100% of the values are less than maybe 108. 0% of the values are less than 92. And anywhere you go along this curve here, you can see maybe 60% of the values are less than 102.5. So that's what a cumulative distribution looks like. Notice the way I've plotted this. So I've plotted our sample values, again, which are all in order, and our cumulative fractions. And I'm using the line style called steps mid. And this is how we get these staircase kind of steps going up like that. And mid means let's put the data point in the middle of this line here. So our first data point at the 0th data point here is at 92, or very close to 92.5. All right, so we can plot that sample again, and what we really want to do is compare it to the parent population. So we want to plot the cumulative distribution function of a Gaussian distribution, of a normal distribution. So the way we're going to do this is I'm first going to define a function. This is a function called CDF, and I'm going to use the lambda operator in Python to do this. So the lambda operator is just a quick way to define a function without using a def statement. It's just a one-line way to define a function. So I'm going to have a function that takes one argument called, we're going to call it x for our purposes. And what it's going to return is whatever this statement returns here. So this is going to call another function in SciPy stats norm, the normal distribution. There's a cumulative distribution function. And if you give it an x value, and you tell it what the mean value of your Gaussian is and the standard deviation of that, it will tell you the cumulative number of values that are x or less. So we'll define that function, and then we can just plot all of our x values that we've defined previously, and for each one of those x values we'll get what the cumulative distribution function is at that x value. So if we just plot this, we'll plot both here, and now you can see what we have. So again, this is our stair steps that we had. This is our sample, and then this curve here is our cumulative distribution. Right, so this is what the Gaussian, a true Gaussian with our given mean and standard deviation should look like on a cumulative plot. So again, if you go up halfway here, right, remember we put our mean value at 100, so half of the values are below 100, half of the values are above 100, and how quickly this line slopes, whether it slopes like this or if it slopes very quickly, that's what actually our standard deviation is. So if you move over one standard deviation, it's going to drop off. Now, one thing to keep in mind is that I've created this sample randomly. So you might have created your sample randomly, and you might have a different plot now on your screen, but you have the same basic idea. You have some kind of a data sample with all these steps in it, and then you have this nice smooth curve from your Gaussian function. Now, the question is, are these two samples consistent? There's a simple way to actually look at this, which is to look at what the difference is at each one of these x values between our sample and the cumulative distribution of the parent population. So basically we're just looking at what this vertical shift is between our two. And we'll find what the greatest shift is, and that'll tell us how deviant our sample is from the parent. Because obviously if it was perfectly represented, if we just if we had a large sample, it should perfectly follow this orange line here. But by random chance we just happen to pick, or I happen to pick, the computer happened to pick some values that have a distribution, in this case, that are just maybe slightly shifted over from this line. Yours might be shifted differently, depending on how you do things. All right, so what we want to do now is we want to measure what this the maximum vertical offset between our sample and the parent population are. So here's what we're going to do. At every point, we can calculate what the difference is. So we're going to define a diffs variable. And what we're going to do is we're going to calculate what the parent population cumulative distribution function should be for each one of our sample values. And we'll just subtract that off from what our cumulative distribution is, which is our cumulative fracs. So that's going to give us all the differences for every one of our sample bins. We're going to get the difference. And then it just means that all we need to do now is just find what the maximum difference is. So I'm going to find the index of the maximum difference, and I'm going to use the absolute difference. I don't care if this our plot is above or below this line, so we're going to use the absolute numpy abs difference of the difference, and we're going to find the index, which is maximum. So we're going to use argmax. All right. So I'll get the index for whichever one of these bins has the maximum shift. And then I want the value. I'm going to call this capital D. That's going to be the value of this shift. So again, that's just numpy abs. And then just take our diffs of I. And then what we can do is we can actually just plot a line. We're going to plot a green line that just connects the sample that we have from the parent population. We'll see what that visually looks like. So we're going to use plt plot, and we're going to take our sample values, and we want the ith value of our sample. I'm going to do it like this actually. The ith value, we want it twice, so I'm going to send it a list of two i's. And then we're going to have our cfrac, the ith cfrac, and then the CDF value at the I sample. And if I plot this now, there's our green line. So just to label this up, the x label is just whatever our value is from our sample. And the y value is just to remind you, is the fraction of the sample less than a given value. I spell it right. Okay, there we go. So for a given value, we can look at where our sample is, and we see the fraction of the sample that's less than this value, 0 starting here. Nothing's less than that. And then here's our green line. This is showing you where the maximum difference between the sample we measured and the expected value. All right. So you can see the nice thing about a cumulative distribution here is that I happen to have drawn randomly a distribution which is just kind of runs parallel to this line. And that's basically telling us that the distribution that we expect to get from our parent population includes a few values that are smaller than our sample. If our first sample was not here, if our first sample was over here, then you can see what happened. All these values in this whole population here would shift up, right? We'd shift up by 1 if there was one more value down here. So that would just shift this whole thing basically to fit this line. So by random chance, we just don't happen to have one more value down here in this low end that we could have, but that makes sense. This is a small sample size. The other thing to know is that if we had too many values at the high end or not enough values at the high end, again, there'd be a discrepancy on this high end. And same thing for in the middle. So at any point along this curve, you can say, how do these values compare? Do we have the same number of values to this point as we would expect? So what we've done now is at the heart of what is called the KS test. So what we're going to do again is we're going to try and reject the null hypothesis that our sample is drawn from some parent population. And the way we can do that is actually just by looking at this vertical offset that we just calculated. If we can say that that little green line is larger than we would expect just by random chance, then we'll be able to reject the null hypothesis, and we'll say that, hey, our sample was not drawn from the same parent population. There's a lot of literature out there about the KS test. This is a very, very, very common test. You see it a lot in astronomy, in fact. I'll give you a couple sources here that you can check. There's a nice Wikipedia page about this. I'll also point out there is a page from NIST. If you don't know what NIST is, this is the National Institute of Standards and Technology. And they actually have a lot of good stuff on here. Some of this, the web page is admittedly a little bit, they're not as visually appealing as modern web pages, but they have good information on here. And they have a whole statistics handbook that tells you a lot of the different standard tests that we do in statistics. So there's a nice description here of what you're doing, and they explain this whole idea of what your null hypothesis is, and what happens, how do we reject our null hypothesis, and how do we do that test. And this is a description of actually what we're just looking at, using cumulative distributions to find this maximum difference between the expected distribution and the sample distribution. And then it'll tell you that, hey, if this value is greater than some value, then we'll be able to reject the null hypothesis. So check out this information on these links. Of course, Python comes with this. So KS test is built into Python. It's actually in the SciPy package. So if you go to SciPy stats and run KS test, you can give it a sample of values and whatever you think your cumulative distribution function should be, and it will tell you the results from a KS test. And it gives you two numbers here. It gives you the statistic, and it gives you a p-value here. Okay, so what do these mean? Well, the KS statistic is the maximum absolute distance between the two curves. That's what we just calculated here. That's our capital D. Right? So this value here, 0.20337, 0.20337, same value. So that's our statistic. It's just how far apart are those two cumulative distributions. So what's the maximum absolute difference between them? So the p-value, this is the more important value if you're trying to understand what's the significance of this. So I have some number, 0.2. Does that mean that our sample is not consistent with a Gaussian distribution? Yes or no? How do we know that? Well, the way you can do this is you can just do random drawing. So take 20 samples randomly drawn from a Gaussian distribution and see what your statistic is, and then do it again, and then do it again, and do it again, and you'll get some distribution of d values. And if you can plot those, that will tell you what you expect by random chance to get. That's the expected random distribution. And if you get a d value which is outside of that distribution, then you can say, hey, it's unlikely that your sample is drawn from this parent population. So if you do that, you can actually figure out what the probabilities are, and that's what p-value is. So p-value is the probability that a random test would have a statistic as large or larger than the value that we obtained. So what is the value? The odds of getting a d value of 0.2 or greater? There's a 33% chance. That's what this is telling us. And that's actually a pretty high percent chance. And it should be, because we know actually that the sample is drawn from Gaussian distribution. So what you want to know is how can you, what kind of a p-value would you need to reject this null hypothesis? And what you'd need ultimately is you need a p-value that's about 0.05 or less. If your p-value is smaller than about 5%, there's a less than a 5% chance that it's randomly drawn from that parent population. That's when you can start rejecting it. Sometimes you might want to use a more stringent test, but that's kind of the default values. If it's less than 5%, you can say it's unlikely to be drawn from the parent population. All right, so a couple things to keep in mind when you're doing a KS test. Sample size matters. The more data points that we add to our sample, the less likely it is by random chance that we're going to have a certain d value. So that's going to affect our p-values ultimately. And also it depends on what that parent population's distribution is. For what we've done so far, we've basically been assuming we have a Gaussian distribution, so we can interpret this d value as having some probability. But if we didn't have a Gaussian distribution, then there's the odds of getting a given KS statistic might be different. So if we had a Poissonian distribution, or if we had some other just completely random distribution, we would have a different p-value for the same number of data points and the same d value. So keep all this in mind, especially keep in mind the fact that you can use a KS test to reject the null hypothesis that two populations are drawn from the same population, but you can't use it to prove two populations are from the same population. That's a common mistake in astronomy, and I don't want you to make that. So there's a lot more information out there about the KS test, so I suggest you look over that and enjoy.